To summarize, our foam chunk at the point x0, y0, point on the surface x0, y0, f of x0, y0, has a slope relative to displacement in the x direction of about 1/4, a slope relative to direction of displacement in the y direction of approximately 1, giving us a unit tangent vector, 2 unit vectors, and let me note here that these are not unit tangent vectors, these are just plain unit vectors, and they're not unit vectors at all. We go a unit distance in the I direction, unit distance in the J direction, and so forth, and I just recognized that mistake. In any case, again, our foam chunk, we have a slope relative to displacement in the x direction, a slope relative to displacement in the y direction, that go together to give us a normal vector that allows us to define a tangent plane. If we specify a unit vector, then we can ask what is the equation of this blue line, what's the nature of this blue line that corresponds to slicing the foam chunk in a vertical plane parallel to the u vector. If we slice the chunk, we find that this blue line has an angle phi with respect to the xy plane, and that angle we claim to be the slope, to be the directional, that line we claim to have a slope equal to the directional derivative in the direction u of whatever function f of xy it is that's represented by this chunk. This directional derivative is the rate at which the value of the function represented by this dimension changes with respect to motion in the direction of the u vector. So we have the change in the value of f divided by the displacement in the direction of the u vector, giving us the slope, and that's exactly the meaning of our directional derivative.